That is the significance. Yeah, you have spotted the right. That's why I've highlighted this is this method, because you have to understand what is the. Okay, let us see the saving features. So first thing of TPU version 1 is that they are operating on integers. 8-bit integer supported TPUs improves efficiency over 32-bit floating point number. So advantage of operation you can see here compared to 16, even compared to 16-bit. Then what to speak of 32 bits? Here it is so much more efficient. It's 6 times advantage in energy for multiplication, 13 times for addition. And second thing is TPU uses dedicated memories, also called explicitly managed memory. So we are all have background in CPUs where we are used to hardware managed memory, also called implicitly managed memory. I'll show that first here. We are all used to this cache hierarchy, which is managed by the hardware. And hardware means, for example, hardware will use a policies such as replacement policy, cache block size, and inclusive, exclusion. And as a user, you don't have to worry which data will get stored there. For example, you cannot write an instruction that store this data into L1 cache. It is like invisible to the user. And GPU has a mix. In GPU, shared memory is user managed or explicitly managed, or also called software managed. And there is L1 cache and L2 cache, which is hardware managed. So, and of course, GPUs have a big RF. GPUs have inverted cache hierarchy where RF is much bigger than the L2 cache. So now in TPU, all the accelerators you will see, they will always have explicitly managed or software managed memories because they don't have a general purpose feature. Here in TPU or other accelerator, you know the workload. So when you know the workload, that means user knows I will use this hardware for this workload. Let me allow the user to control what data gets placed where. That's why all of them explicitly managed memories, or which also called software managed. So let us go there. Now TPU uses dedicated memory, also called explicitly managed memories. For example, here we have 24 megabyte of dedicated buffer and 4 megabyte of accumulator buffer. TPU invests resources and arithmetic units in dedicated memories. TPU has 60% of the memory and 250 times arithmetic units of a server class CPU. So this comparison is for a specific CPU, TPU version 1 compared to one specific CPU, not compared to any CPU. And what that CPU is, I will explain in the next slide. And because it has low precision arithmetic and it uses systolic array, so systolic array has very less area. So now you have a lot of area left, and you use that area for designing ALUs. Whereas in CPU, the philosophy is to just increase the cache size, which leaves very small size for the ALUs or the number of cores. That's why CPUs have very few cores. 4, 8, 16, that's all. Whereas here you can have so many ALUs or so many max. TPU has one large 2D multiply unit, whereas the CPU and GPU, which I will tell what exactly is in the next slide, next presentation, those have only 1D multiply unit. So I think someone was asking, can we use some other architecture than systolic array for doing multiplication? Yes. That's what CPUs do. CPUs don't have systolic array. They have either individual multiply units or if you see vector extensions, AVX, then they have vector units. And now I will just come to that very soon. Matrix multiplies and DNS benefit from 2D hardware. 2D organization enables systolic arrays, which reduce register access and energy. Now, this is the we'll compare CPU with GPU and TPU. The CPUs primarily have implicitly managed memories. You might have heard of the term scratchpad. So scratchpad is not part of general purpose CPU, but if you see embedded system, there you hear the word scratchpad. So scratchpad is explicitly managed memory, something similar to shared memory. But in the high-end processors, servers, you don't find scratchpad. Because general purpose, if I'm purchasing a CPU, I want all kinds of workloads to run on it. There, I don't know which workload it will be, so I don't want to control my caches. Let the hardware control. TPU has software managed memories, whereas GPU has both hardware and software managed memories. So now you can see GPU is neither fully general purpose nor fully custom built. So that's why it has intermediate purpose. Here, okay, just one sentence I would like to. Okay, so conventional CPUs operated on scalar operands. Of course, modern CPUs, they have all the vector extensions, AVX, SSE, AVX 512. I also heard like 1024. And where most recent CPU, if you see IBM's Power 10 and Intel's Sapphire Rapid, they also have matrix extension. That means you can directly multiply matrices. So that is very recent. But I'm here, that's why I've distinguished. This is a conventional CPU. They operated only on scalar vectors, scalar operands. Then GPUs came, which had CUDA cores, which operated on on vector operands. Of course, now GPUs also have tensor cores. If you studied about the tensor core architecture, they can directly multiply two matrices. Each of them is 4 cross 4. And TPUs operate on tensors. So here you can see this is scalar, vector, and matrix. This is the reason why TPUs are very efficient, because they're directly working on matrices. So if your workload is matrix multiplication, what is the benefit of doing scalar multiplication and then accumulating that and achieving matrix multiplication? TPU has one program thread, whereas GPU and CPU, they have multiple threads. A single thread makes it easier to stay within a fixed latency limit because you don't have to switch between one thread to another thread to another thread. You need a fixed latency, especially in cloud scenarios. You have some deadline, which also saves energy. The whole point is keep the control logic very simple. Don't use very fancy functionality. So that's why TPU has no general purpose performance features. TPU drops features required by CPUs and GPUs that DNANs do not use, such as caches. TPU doesn't have cache, at least this version. The later versions have some sort of cache, but not this version. Branch predictor, there is no need of branch predictor. Even GPUs don't have branch predictor. Out of order execution, multiprocessing, context switching. This makes TPU cheaper, saves energy, allows transistors to be repurposed for domain-specific optimizations. So you don't use transistors for just making caches or taking out of order execution, but use them for designing PIUs. TPU achieves 10 times improvement over CPU, GPU just by using a novel architecture, specifically systolic array. So this kind of improvement is very rare. It takes a lot. Those who have worked on Gen 5, they know how difficult it is to you do any optimization and performance doesn't improve. You can, for example, you can reduce the cache miss rate, but to show an improvement in the IPC doesn't come because anyway it's out of order world, out of order core architecture. But here TPU so it's a drastically different core architecture. It's not just minor modifications to CPU. It's a paradigm change. Okay, although I have not discussed brainwave here, usually I do in my regular course, but let us quickly discuss. So brainwave is mapped on FPGA. TPU version 1 is as an ASIC. Brainwave supports 8 or 9-bit or maybe even 11-bit floating point. Here it is 8-bit integer. Here, brainwave, the key idea is to store all the weights on chip. Here, actually, when I say off chip, originally they are stored off chip, and before the multiplication, they are brought on chip. They're not perennially stored, they're not all the time stored in on chip, they're perennially stored in the off chip. Brainwave's key idea is to use a batch size of 1 because so brainwave is focused on minimizing latency, and TPU is focused on optimizing throughput. So here we use more throughput. So here the number 8 is just a number I've taken from their benchmark results. Now core computation pattern, here it is matrix multiplication. That's what systolic array does. And here it doesn't do direct matrix multiplication, here it does matrix vector operation. Both of them use CISC. Here we saw already that we have this number of MAC in it. And here, how many MAC you will have, that depends on your FPGA. For example, these numbers are for static 10. So here it has 80,000 MACs. For certain workloads, it got this much throughput, and here for certain workload, it has this much throughput. Again, this number is not written on the wall. It depends on the workload. Here we have this frequency, here we have this frequency. Frequencies are comparable. As you know, we can't increase the frequency too much because power increases super linearly. And power consumption, this is very small. Here it is somewhat large. Depends on the FPGA. And here, total on-chip memory, you have to add that 24 megabytes plus 4 megabytes. So that's 28 megabytes. And here, the block RAM is 30 megabytes in total.